The topic of today's video will be non-homogeneous linear difference equation with constant coefficients, right? And as we already know that what do we mean by a non-homogeneous equation? That is when the right hand side function is a non-zero function of a difference equation, right? And the last video we discussed a method to determine that particular solution that is corresponding to the term present in the right hand side, and that method was a method of undetermined coefficients, right? In this video I'll be discussing a new method that's called an operator method, right? But before that we should know some basic concepts about two operators, right? So first I will give the definition of a forward difference operator, right? Forward difference operator, and the symbol for this operator is this delta, right? So this operator, forward difference operator, is applied on Yn, and we already know what is Yn. You can say that Yn is a solution of some difference equation, right, which is given in Yn. And what is the difference equation? It is just a relationship between the nth term and its one or more previous terms, right? We call it recurrence relation also. And suppose Yn is the solution of that difference equation, and especially this Yn is also called discrete numeric function, right? Why it is called discrete numeric function? Because its domain is a set of integers, especially positive integers, right? 0, 1, 2, 3 and so on, and its range can be anything, means a real number. Such a function is called a discrete numeric function, right, which has a discrete domain, right, a kind of positive integers. So we can say that this Yn is a discrete numeric function, or roughly you can say that this is a solution of some difference equation, right? So I'm going to operate delta. Delta is a forward difference operator, right? And this is actually equal to Yn plus 1 minus Yn, right? Or I should write Yn plus h, because h is the interval of differencing. H is the interval of differencing, right? And if we take, generally we take in a linear difference equation, we take n equal to 0, 1, 2, 3, 4 and so on. So here we'll have h is equal to 1, because the difference between the successive integer values is equal to 1. So generally we take h is equal to 1, right? So h equal to 1, then this formula reduces to Yn plus 1 minus Yn plus 1 minus Yn. Okay, so this is called the forward difference operator, right? When it is operated on some discrete numeric function, that is just equal to the difference between the n plus 1th value of that function and nth value of that function. This is called delta Yn, right? And you can, in particular, you can say that if I find delta of y0, that will be equal to y1 minus y0, right? If I apply delta y1, that will be equal to y2 minus y1, etc., right? So delta is an operator which operates on a discrete numeric function Yn, right? Okay, and another operator, and one more thing, I should define the higher order derivative also, right? Also, if you find delta square y0, this is the second order forward difference operator. It is very similar to that differential operator, just like you differentiate a function 1 times, 2 times, right? So similarly you can operate this forward difference operator on a function once, twice, thrice, etc., right? So I will write it as this way, right? Okay, and using the value of delta y0, that is equal to y1 minus y0, then taking this delta inside, right, and then using delta y1, that should be equal to y2 minus y1, and this delta y0 should be equal to y1 minus y0, and ultimately I will get y2 minus twice of y1 plus y0, right? So similarly you can find higher order differences also, right? Okay, so this is just the basic understanding of a forward difference operator, and it will be used in this method, right? And there's one more operator that is called shift operator that is also used here. So shift operator, and that is denoted by the symbol capital E, right? And this shift operator, when operated on a discrete numeric function, suppose it is operated 1 times, right, then it will give y n plus 1h, right, or n plus 1. I have assumed that h equal to 1, right? If you operate it twice, it will give you y n plus 2, right? So it appears that the superscript of this capital E goes here, and that is added with this subscript of y, right? So in general, I can write, if I have e to the power k yn, then it will give me y n plus k. So you will remember this formula, right? Okay. So both shift operator and forward difference operator will be the important part of this video, right? And before that, I have to give a relationship between these two. E and this delta are related by some small relationship, and that is relation between capital E and delta, right? So this is a small derivation, and I will start with this thing, this one, delta. Since delta yn equal to y n plus h minus yn, I have used this standard formula, right? Okay, and you can see that this is yn plus h, and using this result, yn plus k can be written as e to the power k yn, right? So writing this in reverse way, if you replace this by, that should be e to the power h y n, right? I have used the shift operator in reverse direction, minus yn, and then taking common e to the power, where is that, h, I think it should be 1, delta, it is delta, so I should take h equal to 1, okay, h equal to 1, h equal to 1, fine, okay. Then take yn common, that will give you e minus 1 yn, right? It means that when you operate this delta on yn, that is equal to the function that is actually the e minus 1 operated on yn, right? It means that these two operators are equivalent, not equal. Delta is equivalent to e minus 1. Therefore, you can say that delta is equivalent to e minus 1, right? And use this symbol here, equivalent symbol. Two operators cannot be equal, rather they are equivalent, right? Okay, so this relationship will also be used in our method, this method, operator method, right? So I will start that method, operator method. These operators will be used, right? Okay, so what is the operator method? I will start with the equation, standard linear difference equation with constant coefficient, non-homogeneous type, and that equation was, consider, the equation was I think that was y n plus k, that was kth order, right? I should start with a simplest example, that should be yn plus 2 minus 4 times yn plus 1 plus 6 times yn equal to, let me write it fn here, right? Or should I write 0 here, right? So this is a difference equation, and you can see that this is a difference equation, this is homogeneous because right inside is 0 and all of the coefficients are constants, right? And this is of order 2 because the difference between this highest subscript and the least subscript, if you subtract these two, you will get 2. It means that this is a difference equation and it has order equal to 2, right? And I will try to convert this equation into a new form, right? This yn plus 2 can be written in this way using this formula, right? So that will become, or e square yn, right? And this can be written as minus 4 e yn plus 6 yn equal to 0, right? And then you can write it as e square minus 4e plus 6 yn equal to 0, right? So you can see that the original difference equation is converted into some new form, and this form is containing operator capital E, right? So first, this is first equation, this is second. So second and one are just the different forms of same equation, right? And again it can be written in a new form. If I use this relation, capital E should be equal to 1 plus delta. If I put 1 plus delta here, and then I will get an equation in terms of delta, right? So that is another way to write it, right? Use capital E is equivalent to 1 plus delta, right? So that will give me, if I plug this 1 plus delta in place of E everywhere, I will get 1 plus delta square whole square minus 4 times 1 plus delta plus 6 yn equal to 0, right? And on expanding it, I will get delta square 2 delta minus 4 delta, that will give you minus 2 delta, I think, right? And from here plus 1, 7 minus 4, that should be equal to 3 yn equal to 0. So here we have got another representation of the same difference equation, right? So 1, 2 and 3 both are different forms of the same difference equation. One was the original, which was containing this discrete numeric function yn plus 1, yn plus 2, right? The second one was containing discrete numeric function yn only, but together with the operator capital E, right? And the third one we are having operator delta, right? It means that we can convert this problem. So far we have been solving this difference equation using our previous method, undetermined coefficient method. Now we will use this operator method, but to use that operator method we should switch our equation to this form, right, in order to use these capital E and delta symbols, right? So in this video I will be converting my equation into this form, right, and then I will be using this theory, new theory, right? So now focusing on the equation when the right hand side is non-zero, right? You know that the right hand side, when the right hand side is non-zero, you first find the homogeneous solution, you call it YNH, right, by equating the left hand side equal to 0, right? And then you find the corresponding solution corresponding to the right hand side term, right? So same is the procedure here. I will first write the standard difference equation in terms of k, right, of order k. So here's the theory, operator method, right, operator method, okay. So it starts with the kth order difference equation, and that is yn plus k, p1 times yn plus k minus 1, p1 is a constant, right, since we are dealing with constant coefficients, and then p2 times yn plus k minus 2, and the last term should be, I think, pk, yeah, pk yn, right, equal to, here we had this function fn, and this was our equation number a, right? Okay, so we are searching the solution for this equation, and first what will you do, I will just convert this equation into this form, capital E form. I can write here or it can be written as, if you see this, just take this k in power of capital E, right, and here I will have yn, right, I am not writing that, plus p1, from here I will get e to the power k minus 1, and then yn, and so on. The last term will be, I think, only pk, and outside will have yn equal to fn, right? So the original difference equation has been converted in terms of capital operator E, right? And now the homogeneous solution can already be found by equating this to 0, right? And yeah, to find particular solution, that is denoted by ynp, what we will do, we know that let me write this whole polynomial as a one function phi e, right, which I should write that first. I will write it here. We know that, okay, I am writing this, replacing this polynomial in capital E, right, by function phi e, right? Not need to write this whole polynomial, full polynomial, just write this phi. Phi indicates this whole thing, right? And yn h equal to fn. Why yn h? Because we know that ynp y and p is the particular solution of this difference equation, and the particular solution when substituted in the difference equation gives left hand side equal to right hand side, right? So that's why I have replaced this yn by y and p and left hand side equal to right hand side, right? And this phi is this thing, right? So in order to find this y and p, I can take this phi here 1 over phi e, right, fn, right? So this is your particular solution, and if you see this very carefully, you will remember that differential equation, I mean particular solution in case of differential equation, as you have studied in last semester, right? We find particular solution by writing this formula, means 1 over that auxiliary equation here, and then we have function here, right? Then we have several methods depending on the fn, right? So same theory will be applied here. I will just write the formulas, not the derivation. In order to see the derivation, you should refer to our video partial differential equations, right? All of these results have been derived there, right? So I will discuss cases one by one, right? So after finding y and p, you just add y and h and y and p, and then you got the solution. You will get the solution, right? So I will start with case 1. If fn, this right hand side of your function, is of special type, that is beta to the power n, right? If you have such function beta to the power n in the right hand side of your difference equation, then this formula will be used. I am going to write that formula, and that formula is, in that case, y and p is equal to 1 over phi e, and here we'll have beta to the power n. Obviously in place of fn I will have this thing, right? And what you will do, you will just replace this capital E by beta, right? So we'll get phi beta, right? And since at this position, please see this step, this is an operator, first thing is that, and this is a function. So do not write this beta to the power n on the head of the operator. That is absolutely wrong, right? So just write this function after the operator, right? This is an operator, okay? And why I am calling this an operator, you see here, what is phi e? Phi is actually a polynomial in terms of e. And what is e? E is an operator. So sum of these all operators will be a new operator, and we denoted that by phi e. So if phi e is an operator, so 1 over phi e is another operator. Just like the if capital D is the differential operator, then 1 over d is the integral operator, right? So that's why this is an operator. So please write this beta to the power n carefully. Do not write this here, right? You should write it here, or you cannot write this beta to the power n before this operator. First you write the operator, then the function, right? And now you replace this e by beta, and now you are free. This is not an operator now, this is a number, phi beta, right? Now you can write this beta and here also, right? Provided the denominator, this denominator, because phi b will be a real number, right? You will replace capital E by this number beta, so this will be a real number, and this real number should not be equal to 0. In that case, this formula will be used, right? And to see the derivation of this formula, please refer to our video partial differential equations, right? Where we have derived all of these formulae, right? Okay. And then what happens when phi b equal to 0? I will write that formula. In case phi b equal to 0, what we'll do, the y and p can be found by this way, n beta to the power n minus 1, and here we'll have phi dash e or phi dash beta, right? First we'll find the derivative of this phi e, right, with respect to capital E, and then we'll put beta there, right? And if again this phi dash beta goes to 0, then the formula becomes n times n minus 1 beta to the power n minus 2, and this will become phi double dash beta if this failure occurs twice, right? So I will be taking examples of this thing first. Example number 1, right? So solve non-homogeneous linear difference equation. I should take that y n plus 2 minus 7 y n plus 1, and here I should have 12, right? 12 y n equal to, let me write it, 1, right? Okay. So solution, you just see that the right hand side is a non-zero. There is a 1 this time, and this is a case of non-homogeneous difference equation. So first I will treat the homogeneous difference equation, that is the left hand side equated to 0, and then I will find the auxiliary equation or characteristic equation and then its roots. So let yn equal to that alpha to the power n, where alpha to the power n is not equal to 0, or I should write h here, is corresponding, sorry, homogeneous solution, that is the solution corresponding to the homogeneous difference equation. Then we get auxiliary equation of this nature, a quadratic in nature, alpha square minus 7 alpha plus 12 equal to 0, right? That is very simple. You just see the suffix, this is n plus 2, so that will be alpha square, alpha and alpha to the power 0, right? So we will be getting a quadratic equation, and then factorizing it, we will get alpha is equal to 3 and 4, I think, yes. So two distinct roots are available, and therefore the homogeneous solution will be C1 3 to the power n plus C2 4 to the power n. This is the homogeneous solution, right? And then particular solution, and we denote that by yn p, right? That is given by that formula, that is 1 over phi e. Phi e is just this polynomial in terms of e, right? Okay, so I will write capital E square minus 7e plus 12, right? Okay, and where is my right hand side function? See the right hand side function, that is 1, right? You should write it here. But we have the formula for beta to the power n, but this is not in that form. So I will write it 1 to the power n, because 1 to the power n is equal to 1. So I can write it this way also, right? So here my beta is equal to 1. So what I will do, I will just replace this capital E by this beta, and I will get, I will write it here, 1 over 1 square minus 7 times of 1 plus 12, right? And that will produce, and this 1 to the power n is 1, so I have written 1 only, right? So it will give you 12 plus 1 13, 13 minus 7 6, right? So 1 over 6, right? This is a particular integral or particular solution, therefore the full solution will be ynh plus ynp, right? And that shall be C1 3 to the power n plus C2 4 to the power n plus 1 over 6, right? Is complete solution. Taking another example, example 2, solve y n plus 2 minus, I will take the same left hand side, yn plus 1 plus 12 yn equal to 3 to the power n, right? So this time I have 3 to the power n in the right hand side. The left hand side is same, so I will write that solution directly, that is yn equal to C1 3 to the power n ynh, sorry, plus C2 4 to the power n. It is a homogeneous solution, right? Is homogeneous solution, and then calculating its particular integral, that is ynp is equal to 1 over, where is that auxiliary equation? I have not written that, so copy it from here, capital E square minus 7e plus 12, and this function, where is that function? 3 to the power n on the right hand side, right? And this time beta is equal to 3, so you will just replace this capital E by 3, but be careful, if you replace this capital E by 3, you will get 3 square, that is 9, 9 plus 12 is 21, 21 minus 21, you are getting 0 in the denominator, right? So you cannot use that rule directly, you have to use that alternate formula when the denominator goes to 0, and that formula is n times 3 to the power n minus 1, right? And here I will have the differentiation of this thing with respect to capital E, that will be 2e minus 7, right? And now try to plug this beta here. Yeah, 2 into 3 minus 7. Now I am not getting 0. So 2 into 3 minus 7, that will be 6 minus 7, that will be minus 1. So ultimately the answer will be minus n times 3 to the power n minus 1, right? So at this point we had the denominator equal to 0, right? So I will write it as phi of e equal to 0, or I should write phi 3, right? Phi 3 equal to 0, where phi e is this polynomial e square minus 7e plus 12, right? Okay, and now you can add these two, ynh plus ynp, that will be a complete solution, right? Taking another example, example number 3, solve yn plus 2 minus 4 times yn plus 1 plus 4 times yn equal to 2 to the power n, right? And writing its auxiliary equation, that will be alpha square minus 4 alpha plus 4 equal to 0, right? That will produce alpha equal to 2 and 2 repeated roots, right? And when you have repeated roots, your homogeneous solution is written in this way: c1 plus c2 times n multiplied by 2 to the power n is the homogeneous solution, right? And now particular solution equal to 1 over this polynomial in terms of e. Here we'll have 2 to the power n, right? And if you put this beta is 2 here, you will get 2 square, that's 4 plus 4 is 8, and minus 8. You will get 0 in the denominator. So you have to use that alternate formula when you write n times 2 to the power n minus 1, and in the denominator you just differentiate it with respect to capital E, so 2e minus 4, right? And now you can put beta equal to 2, but if you put beta is in place of capital E, you are again getting 0 in the denominator, right? So this is the case of failure twice. So I have to use this formula twice. Again I will write n minus 1, this n minus 1 comes here, 2 to the power n minus 2, and the differentiation of this thing will be, I think, 2, right, over 2. Okay, so this is a particular solution, and you can write it as, therefore, yn equal to ynh, that is c1 plus c2 n, and 2 to the power n plus n minus 1, 2 to the power n minus 3. Yes. Okay, so this is your solution, right? And one more thing, you can see that if I multiply these, I will get n square minus n, right? And the first term will be n square into 2 to the power n minus 3, that will be n square over 8 into 2 to the power n, right? That is fine. But the second term will be minus n by 8 multiplied by 2 to the power n, right? Yeah. And that term is actually this term. You see this term. If you open this, you will get two terms, n square by 8, 2 to the power n, that is fine. And the second term will be n by 8, 2 to the power n, right? I am talking about this term, second term. This second term is of the same form of this term, right? Constant multiplied by n multiplied by 2 to the power n. This is, here is the constant. Constant is 1 by 8. 1 by 8 is constant, multiplied by n and multiplied by 2 to the power n. It means that this term is already occurred here, right? So sometimes what you can do also, this is also correct, and again you can write it as, or c1 plus c2 n 2 to the power n, right? And out of these two terms, since second term has already been counted here, so no need to write this term, right? I will get n square over 8, 2 to the power n. This is also acceptable solution, right? Because the term in the particular solution is already occurring in the homogeneous solution, right? So both of these two forms are correct, right? Okay, so I will take another case when right hand side is a function, sine or cos function, right? In that case, what we will do, I will rub this first. case 2, if Fn is the right hand side of our difference equation, equation number A, that is sine, suppose I write sine an, right, or cos an, okay, then in that case y and p equal to 1 over that phi e, okay, and sine an. I am taking only sine an, right. Similar is the case for cos an. So sine an, if we have sine an here, what we will do, we'll convert this sine function into exponential function by using this rule, 1 over phi. You know that the formula for sine theta is equal to e to the power iota theta minus e to the power minus iota theta over 2 iota, right. And then this becomes case number 1. Why? Because you see this, just take this 1 over 2 iota outside, right, 1 over phi iota, and here we have this e to the power iota an, and this can be written as iota a to the power n, so that this is a beta to the power n, right. You need to write this term in form of beta to the power n, so this is a beta, right. And in the second case for this term, minus 1 over phi e will have e to the power minus iota a to the power n. So for this term, beta will be equal to e to the power of minus iota a, right. And then we'll evaluate this as we evaluated in case number 1, right. Okay, and similar is the case for cos n. In cos n, you will replace this by e to the power iota n plus e to the power minus iota n over 2, right. Iota is not present in the denominator in case of cos, and similar is the procedure in case of cos n, right. I will take an example for this. Example number 4. Solve y n plus 2 minus, I should write a small minus 1, or I should write plus yn equal to sine a n, right. Okay. Or should I write sine n only? Sine n, right. Solution. First I will write the auxiliary equation, and that shall be alpha square plus this is alpha square, this is nothing, alpha to the power 0, 1 equal to 0, right. And that will give you alpha equal to plus minus iota, okay. And then since I'm having complex roots, I will be using the homogeneous solution for complex roots case, and that is equal to r to the power n. And what is r? R is actually equal to square root of a square plus b square. A is 0, b is 1, so that will be 1, that will be 1 to the power n, fine. And c1 times cos n theta, cos n theta, and what is theta? Theta will be tan inverse b by a, that will be pi by 2, so cos n pi by 2 plus c2 sine n pi by 2, right. I have directly applied that formula, okay. And yeah, this is my homogeneous solution. Then I will go for particular solution, right, and that should be equal to 1 over, in terms of capital A, it should be e square plus 1, right. E square, you can see that this is 2, that will produce e square yn, and that will produce yn only, right. So ultimately it will be e square plus 1, capital E square plus 1, and here I will have this sine function, sine n, right. Now what I will do, I will replace this sine n by 1 over 2 iota, and this is 1 over e square plus 1, this will become e to the power iota n using this rule, right. And then minus 1 over e square plus 1, and then e to the power minus iota n, right. And then I will evaluate this further, right. So what happens if I just put this beta here? Am I getting a non-zero denominator? You should check it, because beta is equal to e to the power iota, and you will replace it here, you will get e to the power 2 iota, and e to the power 2 iota, okay, that is fine. I don't think you are getting 0 in the denominator, it can be evaluated, right. I will write it here, or I should write that here. So that will give you 1 over 2 iota, and that will produce e to the power 2 iota plus 1, 1 over e to the power 2 iota plus 1 minus 1 over e to the power minus 2 iota plus 1, right? And now I have to take the LCM, right? Okay. Or should I write it as e to the power iota? If I take e to the power iota common, then it will be e to the power iota, e to the power minus iota. Fine. Okay, right. I should do it like this. E to the power iota is taken common, right? And we'll have e to the power iota plus e to the power minus iota, right? And this 2 iota can be taken here, 2 iota, right? So it will appear here 2 iota. I will write it here now, okay. Minus 1 over, and from here I will take e to the power minus iota common, and you will get e to the power iota plus e to the power minus iota. That's also fine. And now what should I do? I should take this 2 iota here inside, and then okay, it will become 1 over, see this, I need this 2 and I don't need this, no, I don't need this iota, right? In order to, I can see that this is a cost function, right? This is also cost function. So iota will be here outside, okay, and I will take this 2 inside, and 2 will appear here. Or should I write it as e to the power iota, e to the power iota plus e to the power minus iota over 2, and since I have put this extra 2, so that will produce 4 here, 4, right? And similarly here also 1 over minus iota e to the power iota plus e to the power minus iota over 2, right? And now this can be written as 4 iota, and this can be written as, it will take an, okay, e to the power minus iota will appear in the numerator, and this will become cos 1. This will become e to the power minus iota plus iota, sorry, it will become plus iota, okay, cos 1, and now cos 1 can be taken common, right? So 1 over cos 1, or you should write it sec 1, sec of 1, and then this iota is also here, okay, and let me take this iota inside, e to the power minus iota minus e to the power iota, okay, and this 4 is also here, so I will leave 1 2 here, take 1 2 inside, and iota inside also, right? Because I need a closed formula, I don't need iota in my answer. That's why this calculation has been done, right? You cannot leave your answer here, right? You have to eliminate that iota. Okay, so this will become sec 1 over 2, and you see this is sine, negative of sine 1, right? So this is your, and this will go in the denominator, that will become tan 1 over 2. This is your particular solution, and you need to get rid of that iota, right? Because the right hand side was sin n, right? There was no iota involved, okay. And now you will just add your homogeneous solution and particular solution to get the full answer, right? Okay, now I will take third case, when the right hand side is a polynomial, right? Okay. Okay, so when the right hand side is a polynomial, we have to first convert that polynomial into a factorial notation, right? What is the factorial notation for a polynomial? I will give some basic understanding of that thing, right? Before actually coming to the case number 3, I will discuss this, right? That is factorial notation of a polynomial, right? So I will write, I will start with this thing. Suppose you have this thing, we are having y, okay, we are having n, okay, n, this thing, this is, you should read it as factorial n r, right? This bracket is for factorial n r, that is actually equal to, that is defined as n minus 1, n minus 2 up to n minus r plus 1. So this is how a factorial polynomial is defined. you should read it as factorial n to the power r equal to n minus 1 n minus 2 equal up to n minus r plus 1, right? So this is a factorial notation, and that is equal to the product of these factors. That's why we call it factorial notation, right? So every polynomial can be converted in its factorial notation, right? And I will give some particular cases of this formula. So if r equal to 0, right, or should I write r equal to 1, right? So you will have factorial n1, right? And you should put this r equal to 1 here in your last term. This 1 and 1 will be cancelled. You will be left with n. It means that only one term is there, right? And if you put r equal to 2, you will get factorial n to the power 2, right? And you should put r equal to 2 here. You will get n minus 1 in the last term. It means that the first term should be n, right? If you put r equal to 3, then you will get factorial n cube equal to n minus 1, n minus 2, etc. Right? So factorial n to the power 4 will be n minus 1, n minus 2, n minus 3, right? And so on. So this is what a factorial notation of a polynomial looks like, right? Notice that this is the factorial notation and this is the standard notation of a polynomial. These are just the factors, right? Okay. And one more thing, can we convert every polynomial in terms of its factorial notation? Yes, right? And I will show it first how we convert a standard polynomial in a factorial notation, right? So taking a small example, conversion of a standard polynomial, you know all of those polynomials, into its factorial notation, right? And this part is very important, how we convert a given polynomial into its factorial notation, right? So I will take, first I will take, suppose you have this n, this is standard polynomial. Note that this is a standard polynomial, but if I put brackets here, this will become factorial polynomial, and that its value you already know, that is equal to n, right? Okay, so I will start with some bigger polynomial, n square, right? This is a standard polynomial. You want to convert this n square into factorial notation. Note that here we have factorial notation already equivalent to some polynomial, right? But in this case we have this n square and we want to convert this polynomial into factorial notation. So what I will do, I will write let n square, this is a standard polynomial. I am trying to convert this standard polynomial into factorial notation, and since it is of degree 2, so I hope that the factorial notation polynomial will be also of degree 2, right? And that is this a factorial n square plus bn plus c, right? Because we don't know what is the value of a, b and c, we will find the values of a, b and c, right? But clearly here we have degree 2 polynomial, this should be degree 2, that is obvious, right? First thing is that. And then using the values of these things, you can see it from here, you will use n minus 1, and this factorial n is equal to n, right? So b n plus c, right? Now you have a relationship, and using this you can find the values of a, b and c. If you equate the coefficients of n square and then n and then constants, right? If you equate coefficients of n square, you will get a equal to 1, right? And then you equate the coefficients of n, you will get minus a plus b equal to 0, minus a plus b equal to 0, because the left hand side is not containing any n, right? So a is 1, so b will be equal to 1, and equating constants, that will give you c equal to 0, right? So this was your actual polynomial in a standard notation, right? And you wanted to convert it into factorial notation, so that should be written as n square is equivalent to or equal to this notation. What is a? A is 1 factorial n square, plus b is 1 factorial n, and c is 0. So this is your conversion, This is the original polynomial in the standard notation, and for this the factorial notation is this, right? So this is how the process is used. If you have n cube here, you will replace n cube, you will write n cube equal to a factorial n cube plus b factorial n square plus c factorial n plus d, and then you will compare to find a, b, c and d, right? So this is the process by which we convert a polynomial into a factorial notation. But the point is that why we convert a polynomial, a good polynomial, standard polynomial in factorial notation? Why? Because the reason is that since we are going to use this operator method, E delta method, right? So these operators, especially E and delta, behaves as a differential operator d by dx, provided in the case when this polynomial is present in its factorial notation, right? So that's why we convert a polynomial into its factorial notation, because we are familiar with the theory of differential operators. It is very easy to differentiate a function, right, as compared to finding its forward difference operator. That is a long process. So we will convert our polynomial into a factorial notation in order to use that theory of differential operator, right? So remember one point, the key point is that, or the idea of converting a polynomial into its factorial notation is that in order to solve a linear difference equation, whenever the right hand side is a polynomial function, right? And we know that for a polynomial function, if you convert that polynomial into a polynomial of factorial notation, then we'll use the theory of differentiation, right? And all of us are very familiar with the theory of derivatives, right? I will take an example of this thing. Example number, I think that was 4th example, and this should be 5. Okay, 5 examples. Solve, and I must write that I must write that theory first. Case number 3. Case 3. If the right hand side of your difference equation, non-homogeneous difference equation, is some polynomial, let me write it Gn, where Gn is a polynomial, right? Then particular solution equal to 1 over phi e, okay, and here we will have this Gn, this polynomial, right? And in this case use E equal to 1 plus, is equivalent to 1 plus delta to get a new function psi delta in the denominator, right? Because E will be converted into delta, right? And then apply binomial expansion, and then apply binomial expansion. You should take that denominator here in the numerator and then apply the binomial expansion to get the powers of delta, right? To get ascending powers of delta, ascending powers of delta, right? And but to really operate those deltas on this function Gn, this polynomial should be converted into its factorial notation, right? In that case, delta behaves as d, right? And this is actually the goal of changing a polynomial into a factorial notation, right? So that we can use the theory of derivatives, right? Now I will take an example of this thing, and I will try to explain this concept in my example, right? So example number 5, solve y n plus 1 minus yn equal to, I am taking a polynomial n square plus n, right? Okay. Solution, its auxiliary equation will be alpha minus 1 equal to 0. You can see that this is the first order difference equation, and that will give you alpha equal to 1, and then you will write your homogeneous solution as c1 1 to the power n, and that will become c1 a constant, right? And now I will come to the particular solution point, right? But see this polynomial, this is not in its factorial notation. I need to convert this polynomial into its factorial notation so that I can use the theory of derivatives, where delta will behave as capital D, differential operator, right? So I will first convert this polynomial into its factorial notation, right? So convert n square plus n into its factorial notation, right? And how that conversion is done, we use let n square plus n equal to a factorial n square b factorial n plus c, because this is a quadratic, or you can say 2-degree polynomial. So I have written a 2-degree polynomial in factorial notation, right? And I know that this factorial n square is nothing but n into n minus 1. This factorial n is nothing n and c, and here we will have n square plus n. And now I will start comparing the coefficients of n square, n and constant. If I compare the coefficients of n square, I will get a equal to 1, right? A equal to 1. And if I compare the constant terms, see the constant is c, and there is no constant, c will be equal to 0, and now b is remaining. And if I compare the coefficients of n, that will be 1 equal to minus a plus b. So b minus a equal to 1, and that will give you b minus a equal to 1, and we know that this is 1, so b will be equal to 2, right? B is equal to 2. Okay. So a, b, c are calculated, and I will plug these a, b, c here, right? Therefore, n square plus n is equal to factorial n square plus 2 factorial n, right? So I will be using this polynomial in factorial notation as my right hand side, right? Okay. Therefore, yn p equal to, see this, that should be 1 over e minus 1, 1 over e minus 1, and in the right hand side I am having that n square plus n, but that should be replaced by this n square plus twice of factorial n, right? I will write that in bracket. Okay. And the method says that you should replace this capital E by 1 plus delta. So you will write 1 plus delta in place of capital E, and ultimately we will get delta in the denominator, right? This factorial n square plus twice of factorial n. And I have used, since E is equivalent to 1 plus delta, right? And 1 over delta to 1 over delta factorial n, right? This is a linear operator, and that's why it's get distributed with these terms, right? But as I said, that the method consists of using that binomial expansion in ascending powers of delta, but there is no scope to use that binomial expansion because I am getting only delta here, right? So I cannot use actually that binomial expansion. But remember that in this scenario, when you have this polynomial in your factorial notation form, delta is equal to or equivalent to a differential operator dy dx. So what should be 1 by delta? It should be an integral operator. So what I will do, I will just integrate this, right? Okay, because here we have this 1 over delta, right? Okay, so integrating this, I will get factorial, and do not remove these brackets, right? N cube over 3. Okay, and on integrating it, it will give factorial n square over 2, and this 2 and 2 will be cancelled, right? And then using the value of factorial n cube, right? As I wrote the values of these standard factorial notation polynomials, and that is n minus 1, n minus 2, right, over 3, and this 2 and 2 is cancelled, and this should be replaced by factorial n square n minus 1, right? So this is a particular solution. Or you can take n minus 1 common, and you will be having n minus 2 over 3 plus 1, and on simplification it will give you n plus 1, yeah, n square minus 1 over 3, right? So this will be your particular solution, and then on adding you can write your complete solution, right? Okay, so I will take one more example in order to see that binomial expansion in my particular solution, right? Example number 6, yes. Solve. I will change the left hand side. I should get yn plus 1, and if I use yn here only, plus yn equal to, I use that n square plus n only, right? Okay, or I change it? I should use n square plus 2n, right? Okay, then homogeneous solution, I should write it directly. That should be yn h. I think minus 1 will be the root, and in that case I will get c1 times minus 1 to the power n, right? This will be your homogeneous solution. And particular solution will be, but before actually calculating its particular solution, I should first convert this into factorial notation, right? So using that same logic, let n square plus 2n, because this is a second degree polynomial, so a standard second degree polynomial is this, right? And a n minus 1 plus b n plus c, and this is n square plus 2n, and then equating the coefficient of like powers of n, I will get a equal to 1 and c is obviously 0, c equal to 0, and b minus a equal to 2. So b minus 1 equal to 2, so b will be equal to 3, right? B is equal to 3, and therefore your polynomial n square plus 2n, that is a standard polynomial, that is now converted into factorial polynomial n square plus 3n, right? Okay, and now I will start evaluating that particular integral. So 1 over that, what is that? E plus 1, e plus 1, e plus 1, and here I will have factorial n square plus 3 factorial n, right? And I will replace this e by 1 plus delta, right? And that will reduce to 1 plus delta, 2 plus delta, right? And here I will have this factorial n square plus 3 factorial n, right? Since e is equivalent to 1 plus delta, okay, right? Now I can use that binomial expansion because I am having two sum terms here. In order to use that binomial expansion, I should create 1 here, and I should take this 2 common, right? So 1 by 2 will be taken common, and in the bracket I will be having 1 plus delta by 2, and that 1 plus delta by 2 should be taken here in the numerator, right? Minus 1, and here you are having this thing, factorial n square plus 3 factorial n, right? Now you will use that binomial expansion, 1 plus x to the power minus 1, that is 1 minus x plus x square minus x cube plus x to the power 4, and so on, right? But the question is that up to how many terms you will write this expansion? I will write only 3 terms. Why only 3 terms? See, the power of delta is square. And why I stopped this expansion here? Because the polynomial is of degree 2, right? And if I write the next term also, that will be delta cube over 2 cube, and delta cube means you have to operate that delta cube on this factorial n square, right? And that will be equal to 0, because in this scenario, when you have your polynomial in factorial notation, is delta is behaving as capital D, differential operator, and a second order polynomial when differentiated thrice will give the result 0. So that's why I am avoiding all the next terms, right? I am stopping it here, n square plus 3 factorial n, right? And you will take all of these terms inside, so we'll get 1 by 2, and when this term is taken here, this is equal to factorial n square plus 3 factorial n. When this whole term is taken with this delta by 2, delta means the differentiation of this thing, we will differentiate it, and this will produce, see very carefully, 1 by 2 is still there, minus 1 by 2, delta operated on this term will give differentiation of this thing, that will be twice of factorial n, right? Okay, and when this delta goes with this 3 factorial n, that will produce 3, so that will be minus 3 by 2, I think, because 1 by 2 is still there, right? And when you operate this delta square on this, double differentiation of factorial n square will give you 2, right? And you already have 1 by 2 square, so 1 by 2 square and 2, and double differentiation of this 1 degree polynomial will be 0. So ultimately I will close the bracket, right? So 1 by 2 and Remember this formula. Factorial n square is nothing but it is n minus 1, right? And this is 3n minus this 2 to be cancelled, 3n minus n, 2n, and that will be 2n, right? And minus 3 by 2 plus 1 by 2, that should be minus 2 by 2, and that should be equal to minus 1, right? And ultimately it will be equal to 1 by 2 n square plus n minus 1, right? So this is a particular solution where you have used that binomial expansion also, right? Taking the last case, case 4, when the right hand side is a mixed function form, beta to the power n multiplied by some function, right? Case 4, okay. Case 4, right? So if the right hand side is, if fn is equal to beta to the power n multiplied by some function, and let me take that function hn, right, where hn is any function. Any function means sine function, cos function, or in third case it is a polynomial, right? Because this method is not used for all of the functions present on the right hand side. We have some special functions on the right hand side, then only we can use this method, right? It's not like that you have log on the right hand side and you will apply this method, no, right? Is any function discussed in previous cases, right? Previous cases, okay. In that case, the particular solution is given by 1 over phi e was the function, and here we'll have beta to the power n h n, and what we do, we just operate this beta by replacing this capital E by beta e, right? And this beta to the power n goes out of the calculation. You will write that here because it has been operated, so you will write it here, right? And here you will be left with this hn, right? And for this hn, that depends on the nature of the hn, right? If it is sine or cos, or it is a polynomial, then the treatment will be given according to the nature of this hn, right? So this is the last case when the right hand side is a function which is actually the product of two functions, the exponential function multiplied by some polynomial or sine or cos function, right? So I will take one example of this also. Example number 7, solve. Let me write, I will write that y n plus 2 minus 3yn plus 1 plus 2yn and equal to, I should take the function of this form. If I take 1 to our roots, okay, 3 to the power n, and let me take this n, right? So you can see that this is beta to the power n, and this hn is actually a polynomial, right? Okay, solution. So first I will write the auxiliary equation, and that shall be equal to alpha square minus 3 alpha plus 2 equal to 0. I think 2 and 1 are its roots, yes. So that will produce alpha equal to 1 and 2, right? And therefore your homogeneous solution will be of this form, C1 plus C2, 2 to the power n, right? And then you will find your particular solution, writing 1 over, say this e square minus 3e plus 2, and here you have your fn this way, right? 3 to the power n. And according to this rule, what you will do, you will replace this capital E by beta E. So I will be replacing this capital E by 3e because beta is equal to 3, right? So ultimately I will got this 3 to the power n will be here, and I will get 3e whole square minus 3 times 3e plus 2, right? And here I will be left with this n. So 3 to the power n has been operated. First thing is that, and no need to write that beta to the power n after the operator. You need to write this before the operator because this has been operated, right? Now you will focus on this part only. You will operate this on this function n, and this is a polynomial, so I will replace this polynomial by a factorial notation polynomial, and then I will use that expansion method, right? On solving it, I will get 9e square minus 9e plus 2, right? I will write that 3 to the power n 9e square minus 9e plus 2, and here I have n, right? I have to rub that first. yn p equal to 3 to the power n, and yeah, 1 over 9 1 plus delta square plus minus 9 1 plus delta, and then plus 2, right? And here I have n, right? Since e is equal to 1 plus delta, and then 3 to the power n, on simplifying it will give you 1 over 9 delta square, right? And then 9 and 9 will be cancelled, but 2 will be there, okay? And this will give you 2 delta, means 18 delta. 18 delta minus 9 delta, that is 9 delta, right? And here you will have n, right? And now converting this n into its factorial form, and I already know that this n is equal to factorial n, right? So I will replace this by factorial n, right? Because as you know that n is equal to factorial n, right? Okay. And then taking 2 common, because I need to use that binomial expansion. In order to get a binomial expansion, I should create a 1 here, and I should take 2 common. So 2 will be taken common, and I will be having 1 plus 9 delta square, 9 delta over 2. And here I am having a 1 degree polynomial in factorial notation. Now I will apply binomial expansion. After taking this in the numerator, that will become minus 1 power, and 1 minus 9 delta square plus 9 delta plus over 2, and the another term will be plus the square of this thing, but there is no need to write that term, because on squaring this term we will get delta to the power 4, delta square and delta cube. All of those deltas are having a power more than this, because this polynomial is of degree 1, so we actually don't need to write that term, right? So I will terminate this series here, and here we have this n, right? And now I will take this n inside, and this will give you 3 to the power n by 2. Taking n here, this will give you n factorial n minus 9 times of 2. Delta square of this thing will be 0, and minus that will be, you will be left with minus 9 by 2. Delta of this thing will be 1. So ultimately you will be having this thing, right? And you know that the value of factorial n is equal to n, right? So this is your particular solution, and the complete solution can be written as by adding these two solutions, right? So this is it, how the operator method works. Note that this method has some limitations, right? It's not like that every time you can apply this method when the right hand side function is of any form, right? In the next video we'll be taking another method to solve a linear difference equation with constant coefficient. Whether it is homogeneous or non-homogeneous, there is a separate method. There is a very powerful method to solve a linear difference equation, that is called generating function method, right? And that will be part of our next video. For this video, thanks.